Pretty exciting moment here, people. Right, so we're a long way into the course. This is kind of 9/13 or something. And we're about to get our second factorization, right? So we had LU decomposition. Pretty good stuff. Workmanlike kind of thing. But very nice. Rectangle equals triangle times triangle. We've just gone through the gram-schmidt process. It's again kind of a workmanlike thing. It sort of does a fairly strategic job. It's not sort of a secret of the universe kind of thing. We'll get to those. Monks will calm down a little bit over there. They're mumbling something about diagonalization. I don't know what that is. Anyway, so but it's exciting. It is a fact. So we can turn the gram-schmidt process into a factorization, and it is. It's a nice day for us. So the factorizations of matrices, that's a huge part, now I'm just doodling, a huge part of linear algebra, understanding what we can do with matrices. Just having them unlocks a tremendous amount. And we will get quite a few more in the last part of the course. There's sort of a whole batch that could come later on, when of course you take advanced matrixology, as you just further your understanding of the greatness. Okay, so that's the story here, right? So we love to use matrices to encode our methods. If we can do that, right? We used elimination matrices at one point. That helped us see that we could get to LU. If we can do a rotation, we'll use it and we'll make a matrix do that. There's lots of there are many examples where we can describe it as a process, perhaps. Maybe it's sort of a sequence of algebraic steps, but if we can turn it into a kind of a product, a matrix that you multiply another matrix, right? That sort of make it into a contraption, then that's pretty good. Okay. So it's empowering is the word here. We're all about empowerment in matrixology. Superpowers. Okay, Gaussian elimination. Triangle times triangle. So that's the plan. We're going to turn the gram-schmidt process into a factorization of A. And so here it is up here again. A equals QR. So Q and A are the things that are like each other, right? So Q, I kind of want to annotate that. So Q is like A, in that the columns of Q span the subspace that A's columns span as well. Q's shape matches A's. I mean, maybe that's a 2. And this one here is R is a combining matrix. This is unfortunate. I just want to say this is an unfortunate namespace overlap, right? We've already used R for reduced row echelon form, but this is a different R, right? This is not reduced row echelon form sub A, so I guess I've introduced this subscript of the matrix for which we're computing the reduced row echelon form. Maybe that helps. Okay. All right, so we just got to this story, and this was the projection matrix version, right? So this is an M by M projection matrix Q1. Right. And this is M by M as well. And this is M by M as well. Really excited about eigenvalues. You will be too. Okay. I promise you. Okay. Good. Right? So that's this idea. We get to Q7 and we chop out we take A7 and we chop out the parts of A7 that are pointing in the direction of Q1, Q2, Q3, 4, 5, 6, right? So we chop them all out, and then what's left has to be a vector that's orthogonal to the first 6 basis vectors that we've constructed. So the monks are going to turn up quite a bit with their strange comments, and we've already got this equation. So if you look at this, there are a bunch of A's on the right-hand side, right? So they're here, it's okay, here. But we do have A1, A2, A3. So we could write A1, A2, A3. We could put them on one side and put a whole bunch of stuff on the other side. So may be promising, right? This is what we did with LU. So this is a goal. So express the AI in terms of the QI using it's kind of a column picture thing, right? So the Q, we're gonna have this matrix Q, which is pretty great, right? I'm just gonna color things in because it's fun. So this is gonna be our Q. Just line them up, stack them up, columns. Good. Q's are fun to draw, so this is good. So this is not, we're not leaving things out. So, right, so we're going to put AIs on the left, right? On the left side of all these equations by themselves. And we'll see that even though there's some AIs on the other side, it's okay by themselves. Now we had A equals LU. And when you think about LU, it's the rows of A that are like the rows of U, right? So we're combining the rows of U to make the rows of A. Here we're doing columns. So instead of having LU, we've got QR, right? The R is on the right-hand side. Just going to say it, we'll come back to it. So taking all of this here, and that's what this rearrangement is. Okay, we'll just flip the first equation. The second equation, we've got all of these pieces, we put them on the left-hand side, so there's a plus. We've got these two pieces, put them on the right-hand, on the other side, plus, and then we flip them, right? So the A3 is here. Okay, so this is looking pretty good. We've got A1, A2, A3, looking fairly good. So this is a nice structure, this is a nice structure, but this looks different. That could be the way it is, but we'd like them to be the same. I say need, but okay. So a couple of ways to sort of rewrite what this is, but here's one thing. So let's take the third line here. And so we're going to see the QI as a projection of AI onto the QI direction. All right? I mean, it's true. So the third of these new basis vectors has some part of the old basis vector, the third basis vector. And if we project that old basis vector onto this new one, it'll just bring out the piece that we constructed. Right, let's just do it algebraically. So we're pre-multiplying, so we've got this A3, this business here, and we're going to multiply both sides, pre-multiply both sides by the projection operator for, right, this is the projection operator in the Q3 direction. And if we think of this thing coming through, so there's a, right, so this is a Q3 transpose times Q1. These are at right angles. It's orthogonal. Orthogonal. So we get 0. Right, so there's a plus 0, plus 0. So it crushes those things. And this piece here, that's what all of this is, right? So it's just Q3, Q3, Q3 transpose, Q3 transpose, Q3, Q3. All those pieces are still there. What is, it's kind of a funny thing. So what is this? This is Q3 transpose times Q3. And it's unit vector times the vector itself. Well, normally it's length squared, right? If it was Q3, the vector Q3, length squared. But we have one where the unit vector is, where the length has been divided out. So this is just the length of Q3. It's a dot product. And then we're multiplying it by the unit vector. So we're back to Q3. We'll work your way through it. So we can, right? So we can replace this Q3 with this blob. Maybe I'll do it like this. So, Okay, so this Q3 is here, and then we're going to replace it with all of this. And we'll do that for A2, and we'll do it for A1 as well. So now they look very similar. I mean, they've all got the same structure, right? There's this projection operated in the Q3 direction here, in the Q1 direction, Q2 direction. They're all multiplying A3. So this should start to make sense, right? If we want to make A3 again, well, we project it into the Q3 direction, the Q2 direction, the Q1 direction, and then rebuild it. So another thing is we could just say this is true. This has to be true, right? So what we see makes sense, right? Everything makes sense. A3 has components in, because they're at right angles, it's all good, has components in the Q1, Q2, and Q3 directions. So if we project onto all of those and then add them back up, we'll get A3 again. This is the same as saying we've got a vector in 3 dimensions. Here is it's projected onto the X direction, the Y direction, and the Z direction, which is going to be I hat, J hat, and K hat, and then add those projections back up. We get our vector again. This is really all this is saying. Okay, so we've got that, and now we can see this is a, now we can start to find the factorization. So all that's happened here is it's the same lineup, but the Q1, Q2, Q3, right? And the point is that these are actually just numbers now. So we can do this sort of funny thing, right? This is a projection matrix, but, right, this is m by 1, 1 by m, and m by 1. So this is these are inner products. This is a well-defined matrix multiplication, right? These things all match. Yeah, 1, 1, and 1, 1, 1, da, da, it's all good. We could make a matrix, which is m by m, it's an outer product, and then multiply it by this vector here. Or we could just do the inner product on the right-hand side. Right, so we do this inner product here, we've got some number, and then we just multiply it by a vector. That's what we want to do now. And so we can turn all of this into a column picture. So here's the first expression. So we've got A1, right, this piece. Let's make our Q. And Q1, it's just Q1 times this piece here. Right, and then we have 0 of Q2 and 0 of Q3. For A1, for A2, again, Q1, Q2, Q3, we're making our Q. We want this piece here, and this piece here, and then 0 of Q3. And the last one, same idea, A3, it's Q1, Q2, Q3. We have this much of Q1, this much of Q2, and this much of Q3. So they're the factors. So this is so now we can start to put all of this together. And we get very excited about ourselves. So we're just taking all of these things here and stacking them up. So now we've got the A1, A2, A3, right? So here, here, here. We're going to put them all together. And we see that we have Q. And then hopefully you can see this. These are the vectors. Right? They're sitting here, here, and here. It's pretty great. So in general, this is an m by n, A is an m by n, Q is an m by n, and R is an m by n. So R is a combining, it's an upper triangular combining matrix. So we had a lower triangular one for LU on the left. This is an upper triangular one on the right, and it's combining these columns to give us A, which is columns, right? Okay, so this is pretty good. let's just do an example. It turns out A equals QR, this is amazing, A equals QR will help us very nicely with AX equals B, so it's going to be a fun thing to do. So that's next. And here's a very nice thing we can do. So a delicious way to find R, so this is very important here, is this. So R in principle, right, we've got all these little inner products, here, all these little inner products. Right, we use the gram-schmidt process that's going to give us the Q's. We normalize them, so we've got the Q hats, all these things. Then we could make R, right? So we could make this decomposition, which we'll see has this use for AX equals B in a second, or in the next episode. But let's just go back to our example, and I'll just show you what you get, right? So this is our example. We worked on this, so we started with these guys, ended up with this set of vectors. They're orthogonal and in fact orthonormal, right? It's an orthonormal basis. So we can take these vectors, make an A out of them. We take these vectors, and you have to have the prefactors, of course, you can't lose those, right? So they head off into here, right? We're just going to stack them. I'll put these here, here, here. So that's our Q matrix. And then we have this combining matrix here, which has, again, this upper triangular form. How do you get these? Well, you could either, right, so find R by either computing the inner products, and they're all going to be these sorts of things, right? They all look like Q hat I, A, J, like this, and J's got to be greater than, let me write the other way, right? I has to be less than or equal to J, yeah? So you can compute all these, that's this piece over here, or kind of simply and nicely, we have this R equals Q transpose times A, which is very nice. So I didn't quite explain this. So this is our very nice way of doing it. So here's our formula, A equals QR. Yep. And then we're going to pre-multiply we're going to talk about these matrices a little bit more in a second by Q transpose. And Q transpose Q. So it's the same as the proof we had for, right, so back here we had this proof for why an orthogonal basis, a set of orthogonal vectors is linearly independent. So this stuff here, right, there's this structure in here, this A transpose A, we get out something that is diagonal. Now, if, with the product, right? So, but if we have this special Q matrix, its rows and columns are made of unit vectors. So in fact, we get something even, a very special matrix, which is the identity. This is because Q's columns are unit vectors. Now, we like the identity multiplying something because it's just, right, identity times R is just R, so we're going to swap it around. This R is this R, so R is just Q transpose A. So that's a nice thing. That's just not a, so that's a fairly easy way to get it. You are guaranteed, in fact, to get an upper triangular, so it's sort of a nice thing to do. So this is a exercise for you. Do this. Okay? Right, and check that you get this answer, which hopefully is correct. It should work, yeah. Okay, you can let me know. All right, next.